Hello everybody. We now continue our discussion on the data structures. We started with priority queue and heap, and we discussed heap and heap sort. Earlier in the previous lectures, the binary search trees have also been discussed, and we shall continue to discuss these data structures. In our overall scheme of things, data structures form a core concept by which we design efficient algorithms, and after the initial solution through a recursive definition, its correctness, analysis of recurrence relations, we explore the possibilities and then we decide on the various core methods that we need to design for our algorithm. And among these core methods, one of the most important core method is data structuring. And data structuring comes because of the need to remember past computations and create certain additional computations so that what we do later on becomes more and more efficient. And among the various data structures, the traditional data structures include stacks, queues, lists, arrays, and then to solve certain categories of problems, we really have come to the need for data structures like a heap, a binary search tree, and several other kinds of data structures. Today, we shall discuss an important data structure called priority queue. We have encountered the need for priority queue many times in the past. We know that a queue is the first in, last out strategy, where we insert at the end of a list and remove from the beginning of a list. However, in many cases, the elements of the queue have key values. And these key values which could have an ordering. And because they could have an ordering, therefore, we will require several operations on these queues in addition to the traditional operations of insert, delete, and find. And we have encountered the need for such key-valued retrievals in problems related to sorting, problems related to searching, and then various kinds of optimization problems which we encountered. We also wanted to find the max, the min, the max, and the next max, and so on and so forth problems. We encountered various other kinds of optimization problems, of which we encountered the pole wiring problem, where we had a power source and we had a list of houses with the poles connected, and we wanted to ensure that we did the minimum length wiring or the minimum cost wiring to connect all these houses and the poles. And this was an optimization problem. Then we had our coins problem, where we had to select the minimum number of coins from a given set to meet whatever was our requirement. Moreover, other than these problems, we will encounter various other problems. We have also seen the activity selection problem. So these issues and these problems are very, very important and require us to have several interesting operations. So what are the operations? The operations typically on a key value is insert, delete, max or min, any one of them, because they are ordered by the key value. Then in many cases, these are the two fundamental operators. Then we have update. Then we have a general delete. And the more difficult operation is the find operation. Typically, these are the two classical operations on priority queues. And in many cases, these two operations are also required, but then the more difficult operator, as we have seen, is the find operator. And if we don't require the find operator, then for this, in this case, when we don't require the find operator, this can be implemented as we have seen in a heap, by a heap. But if we do require the find operator, then we may require binary search trees and balanced binary search trees to do. Moreover, the operations could be static or dynamic. That means, static means all the operations are given upfront. We know what to do upfront. Otherwise, dynamic is we have to create the data structure of a priority queue and we don't know a priori which operations will come. So in the static case, we know the ordering. We know that first may be all inserts followed by all delete mins. Or we may know that a series of inserts. So we know upfront what is the initial value. In the dynamic one, it happens online. So all these are our priority queue operations that we have to implement. Given that the priority queue has got these typical operators, insert, delete, min, max, and if required update, and the delete element, here delete means delete element. So if it means delete element, then we could implement it as a heap. We have already seen the heap, and the advantage of a heap is its implementation as a single array, a very compact implementation, and just an array implementation is enough for us to make sure that we have got a heap. So in the heap operations, how do we implement it using heap? We have seen the following: the build heap function. We have seen the insert new element function. We have seen the remove min or the remove max, depending on whether it's a max heap or a min heap. We have seen the update element, but here in the update element, we know that this update element, provided we have pointer or index of node. Similarly for delete element. So these two can be done provided we have already seen these three operations. And in order to do these three operations, we have used the following functions. We required the implementation of a heap. So suppose this is a heap. Suppose this is a heap which is 12, 8, 9, 7, 6, 2. So this heap has got, as we said, it has got two things. One is it's a complete binary tree. And secondly, it has the heap property, and the heap property is that the value of a node is greater than or equal to the value of its two children. And how do we implement the heap? We implement the heap in an array, and we store the elements in these indices of the array. So which means that if I implement the array, and if this is the array, if this is the array with indices 1, 2, 3, 4, 5, 6, 7, then we keep 12 here, 8 here, 9 here, 2 here, 6 here, 7 here. And we have seen the following functions: the insert new, where it inserts at the end, and then we applied the update upward function, which took the heap A and the index of the node n to be updated, and we updated it at the end, and we have seen this in details. Then we saw the remove min or the remove max. This is a max heap in this case, and in the remove max we said remove the root or first element, and then we did the update. After removing the first element, the next step that we did, so this was one step here, this is another step here, so this is one step. Second is replace root by last element, and then we applied the update down function. In the update up function, we move upwards, and we have seen these algorithms in detail. And then we saw the build heap, function, where given all the elements in an unheapified array, we then did a bottom up update down function iteratively. This update down function also is called the heapify function in most literature. And we have seen that each of these operations are: the insert new operation is order log n, the delete remove max operation and maintenance of the heap property is order log n, and we have seen this function is order n, and based on this we implemented an n log n heap sort algorithm. So these three fundamental operations are now doable by a heap function. Now we will see how to do the other functions. That means we will see the update or revise and the delete element function. And in order to see how we do that, we take an example. So let us take an example of a heap. Now in order to do an update, so here in all these cases we need the index or pointer to the node whose value is to be updated. So that means that in all the applications where priority queue is implemented as a heap and the update revise function is to be used, we need to know, because the find operation is order n complexity. So there are various applications, and we shall see both our electrical pole placement problem, which is essentially the minimum spanning tree problem, as well as the coins problem require and have satisfied these properties. So what is the way in which we do this? So let us assume that we are now given that this value is to be updated. So we are given a pointer to this node and this value is to be updated. So let us assume that this value is to be updated to 23. So what we do is we replace this node. So our update function works like this. We replace this by 23, then we check whether this value is greater than its parent or less than its parent. If it is greater than its parent, then we update upwards. If it is less than its parent, then we update downwards. That means in this particular case, if we check that this 23 is greater than 19, then what we will do is we will do update, we will do an update up. And once we do an update up, so this will become 23 and this will become 19. And obviously, since 19 was the largest of the elements, it need not percolate downwards. On the other hand, if suppose we had to replace this 14 by a value, let us say 2, then we find out that this value 2 is less than 23, and because it is less than 23, it satisfies the heap property upwards, so we apply update down, or this is our standard heapify property. And if we do update down, then we compare, we find the largest of the two, and once we find the largest of the two, then we replace this by 4, this by 2, and this is the root, so nothing can be done, but otherwise it would have gone down. So our function update will require the heap and the node, and here we will check whether the node dot key, that means the key value of the node, is greater than parent. If so, update up, and we have implemented update up a comma node. Else we apply update down a comma node, and recursively this will happen. And therefore, this update operation can be done in order log n time. Now, how do we do delete? So, in order to do delete, we will have access to a node. So, suppose we are to delete, we have already done remove max. So, delete is just like remove max. We replace it by the last node in the heap and then do the update down or up accordingly. So, the delete a node, again we need the pointer to the node. So, here is remove the node, replace by the last element of the heap, and then apply this update a of the current node pointer. And once I replace, I also decrement size of heap and I apply the update, which means that if in this particular case I was to delete 19, then I would have replaced 19 by 2. So, I would have then replaced 19 by 2 and this would have become 2. The heap size would have reduced by one element and then 2 would have propagated downwards because 2 is less, and therefore 15 would have come here and my updated heap would be 23. My modified heap would be 23 and then this would become 15 and then this would remain 8, this would become 2, this would remain 4 because after this had become 4, and this would be 3, and the value at this node would have been removed. This again, as you can see, is order of log n. So, now through our heap operations, we can do all these operations, but the only problem is the find operation. In the heap, we have to return a pointer, and this find operation in a heap is order n. So, wherever find operations are required without the index of the array is not known, then it is a problem in a heap. Otherwise, we have all our operations in order n time, and the beauty of this is that it can be implemented in a straightforward compact array. We go back to our electrical pole placement problem, and obviously we know that this is the problem. Sorry, let us just quickly revise the problem. We have got an electrical station S, and we have got houses where in these houses there are electrical poles P1, P2, P3, P4, P5, P6. These are houses, and we have to connect this electrical substation to these electrical poles of each house, and the cost of connection is proportional to the distance from each point, and being electrical lines we can connect it in various ways. So among the various ways of connection, we want to ensure that we will connect it. So if this was one house, this is another pole, this is another pole, and we want to connect it with the minimum length wire, and therefore here is a possible connection could have been like this, like this, like this, like this, like this, and like this. Probably this is one connection. So among the possible connections, and therefore we all know that this is a variation of the minimum cost spanning tree problem, and we have discussed it in details. And in this problem, the solution was a very interesting greedy solution. So we had seen a greedy optimization solution, and this greedy optimization solution used two sets, the set S and T. The set S initially contained this node, let us call this set, let us call the sets a little different. Let us call this set G and T. Then this G initially contained S and the rest of the nodes. So this initially contained S, and from P1, P2, P3, P4, P5, and P6 were all in T. And then we looked at all the edges that go from this set to this set, and we choose the minimum edge. So we chose the minimum outgoing edge, bring that node from T to G, and then continue. And we go on doing this till all nodes are selected in G, and we have proved earlier that this is the minimal cost operation. So now what are our operations? What is the data structure? What is the data structure to use here? As we have already seen earlier, the data structure that we need to use here is the operations are, we will create a set of edges. So our set S, our set R is the set of edges which are going between the G and T. Our set of edges between G and T, the set of edges between G and T is my R, and therefore my operations are insert new. That means whenever I move a node from T to G, or when I initialize it, I will insert something into this data structure. Second, I will need to delete. So whenever I move a node from T to G, the existing edges from G to T will have to be removed. And finally, I will need to remove min. That means I have to remove the minimum cost edge between G and T. So as we have seen that these three operations can all be done in order log n time, and therefore, so our algorithm has in the worst case to do either insert, delete, and remove min. So the number of times it has to do this plus this is not more than the number of edges in the graph. And this, it does not have to do it for the number of nodes in the graph. And each operation being, but whenever it does this, so each operation will require, because the maximum size of that data structure which we store will have e edges. So each operation will require, each operation will be of order e complexity, and therefore my total number of operations is n log e plus e log e. This is my complexity, and obviously n log e is smaller than e log e, so this is the same as order e log e. And since e is equal to order n squared, therefore this will become order of n squared log n. So this will give us an order n squared log n by using this data structure of a priority queue. So here is a problem where I used this data structure. So finally I have decided that I will use a priority queue. So my data structure to be used is a priority queue. And the key of the priority queue is the edge cost. So here is one application of the problem. The other very interesting aspect is when we come to evaluation of the recursion tree. We also know that our evaluation function in general, in our recursive definition, our evaluation function is that we get R of x if the base condition is true. If the base condition is true, we do R of x. Otherwise, if Bx is false, then we will compute, this is Rb, the base condition. Otherwise, our recursive recomposition function, so which is in the recursive case, when the base condition is not true, then we use a decomposition function. So we get the following. We will do the following. Our first step will be, we will get y1, y2 up to yk. We will get this by applying the decomposition of x, and then we will apply the recomposition of x. That means that we will then do the next step, whereas we will get the value, we will do a recomposition of a recursive recomposition of f of y1, f of y2. We have seen all this before, so I don't want to elaborate on this, f of yk, and we will do this, and whatever we get here, this decomposition will be returned. And therefore, this recursion tree basically looks like this. When we build up the recursion tree, then this recursion tree looks like this. So this is how the recursion goes, decomposition goes, and these end up, let us say these are my base nodes. We have done all this before. And after these base nodes are done, then recomposition happens. So these are my recomposition functions, and then I decompose. So each of this is my RB here, this is my RB here, this is my RB here, base conditions, and these are my RR, the recursive recompositions. This is my RR, and each of these are my decomposition functions. So my decomposition functions. Now how do I evaluate this? So my main question is evaluation of this recursion tree. How do I evaluate this recursion tree? Now in order to evaluate this recursion tree, we can apply a depth first search or a breadth first search, or we can do other techniques which I will not discuss, but there are other like iterative deepening, etc. So there are other techniques like iterative deepening which are. So depth first, in this case if I do a depth first evaluation, then it will go in this manner. This is the first node, then it will generate these two, then it will open. So this will be the first node. So let us just do it once more. So this will be done, then this will be done, then this will be done, then since this is the base condition, this will be done. After these two are done, then this recomposition will happen. Once this recomposition happens, then this will be done, then this will be done, then this will be done, then this will be done because these are base, then this will happen, then it will come back and do this node, then this node, and then this node. So depth first search can be implemented using a stack. If I implement it using a stack, and I don't want to go into much details of this, I can implement it, and I can implement this using a queue. But if the most interesting thing is in case we have optimization problems. So this is how we implement by stack and queue. On the other thing, let us come to optimization problems. So optimization problems have the following feature. So optimization problems have the following feature. In the optimization problems, what we have to do, we have min and max. So my recomposition R is either min or max, which means that if I come back to this, then my recomposition functions are min or max. And we know that these are both associative and commutative. That means that if my, just to draw a very simplified version, if something like this happened, and this let us say is a min, and this let us say is a min, and these are my base conditions, these are my decomposition conditions. So this is my D, D, RB, 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 and this is RR equal to min and RR equal to min. Now because this is min, then I can apply, as we have seen earlier, something called pruning. How can we apply pruning? That means, let us assume that we have a cost. So every node has a cost. So let us assign the costs to every node. So this node has a cost 7. This node, as it is a minimization, costs increase. This node has a cost 8. Let us say this has got 9, this has got 8, this has got 9, and therefore this being min will be 8 and this being min will be 8. Now, when I am applying DFS, depth first branch and bound, what is depth first branch and bound? We maintain, as we have seen, maintain a current best initialized in the minimization problem, initialized to infinity. Then whenever we find a solution, we update current best to the better solution. Also, any node which has got cost greater than equal to current best is pruned. Now, if we do this, then in this particular case, how will my algorithm proceed? My algorithm will first look at this node, which is the first node C. Then it will come to this node. My current best is infinity. Then it will come to this node and I have a solution. And therefore, my current best will now be updated to 8. Then it will come to this node, and since this is also a base node, therefore, I am easily going to see that this node's cost is greater, so current best is not updated. Then it will come here, and even this node cost is 9, so it will remain 8. Now let us assume that this was an intermediate node and this was not a base node. So let us just replace this by a node n which has got some children, and this cost is 9. Let us assume that this cost is 9 and this is not a base node. Then when we come here in the depth first search, we will prune this node even though this is not a solution node. So this is how depth first branch and bound works. How does best first branch and bound work? In best first branch and bound, we apply breadth first search. So we apply ordered search using a priority queue of costs, and we apply the following. We remove min, and insert children, and when we insert children into this queue, that means when this node n1 is removed, then we insert these children and we remove the one. So initially insert the children and stop when goal is reached. So how will this algorithm now work with best first search? So If I run best first search, if I run best first branch and bound, so initially my priority queue PQ will consist of this node. So let us number the nodes N1, N2, N3, N4 and N5. So this will have N1. Then I will remove this node. And replace it by its children, and the children will be N2 and N3. The cost of N2 is 8, the cost of N3 is 9. I will remove the one with minimum cost, which is N2, and I will generate its children, which is N4 and N5, and N3 remains. N4's cost is 8, N5's cost is 9, N3's cost is 9. And then I will again remove N4, and once I have removed N4, this being a goal node, I will stop. So here is how I can implement a best first branch and bound algorithm, which will have all the prunings that a depth first branch and bound can do, but by an implementation of a priority queue. And this is what we had discussed earlier, and we shall now see how this works in one problem that we have solved before. So how does best first search using priority queues work? So what is the algorithm? Our algorithm is as follows. Our first step is initialize. So Q is equal to the start node. That is the start node of the recursion tree. The second is remove from Q the node N with lowest cost. We are solving a minimization problem. For a maximization problem, we have seen what we have to do with maximum. Remove from Q a node with lowest cost. If N is goal, stop with solution. Here, if Q is empty, fail. Because if Q is empty, there is no node, so we fail. If N is not goal, then generate successors of N, node N, using the decomposition function. So using the decomposition rule, we generate the successors. So using the decomposition rule, let them be N1, N2 up to Nk. Insert or update so what we say is that if Ni is not an element of Q, insert Ni in Q. If Ni is an element of Q, update cost of Ni in Q. And then go to step 2. So this is how best first search is used using a priority queue. Let us see how it works for a generic example. So let us have an example like this. Let us create an example. Let us create an example where we have nodes n1, n2, n3, n4, n5. This n6 is a base node, leaf node, n7, n8, this is n9, this is n10, this is n11, this is n12, this is n13, this is n14, and this is n15. And let us assume that the solution, the costs at every node are 2, 3, 4, 8, 4, 4, 9, 10, 7, 6, 7, 5, 6, 8, and 9. So we know that my optimal cost solution is here. So I know that my optimal cost solution is here. My optimal cost solution is this. So how will this algorithm now work? This algorithm, initially my queue will consist of n1 and its cost is 2. The next step, what will happen is, this will be removed. I have drawn a tree. It could also be a graph, but I am just simplifying it with a tree. So queue n1 will be removed and n2 and n3 will be put into the queue. So what will happen is, queue will now become n2 of cost 3 and n3 of cost 4. After this, in the queue, n2 will be removed, and now the queue will consist of n3 of cost 4, n4 of cost 8, and n5 of cost 4. Next, the queue will now have, let us remove n3. So after I remove n3, I will have remaining n4 of cost 8, I will have n5 of cost 4, I will have n6 of cost 7, I will have n7 of cost 5, and I will have n8 of cost 6. After this, n5 will be removed, and after n5 is removed, in this whole example, what we will really have is, after n5 is removed here, when n5 will be removed, n10, which is my n10, will come back here. So among all these things, I will have n10 of cost 4, and that will be the minimum cost, and I will remove n10 and get the solution. As you can see, this one will achieve pruning, and no other node whose cost is greater than the goal node solution will ever be seen by this. And this is implemented as a priority queue, and as you can see, this implementation, this priority queue will be a priority queue with functions insert. This is the min priority queue, delete min, update. And this, each such operation, if there are total of n nodes expanded, by in this step, if in step 2 does n times, then this algorithm will work in total of n log n steps. So this is best first search. In many cases, this has got, in a maximization problem, there are certain variations. And one of the problems that we have seen was our coins problem. You remember our coins problem? The coins problem, we had a set of coins C1, C2 up to Cn and a value V, and we were to find the minimum number of coins to get the exact value of V. So that was my problem. So in order to implement this, we had used many definitions, of which let us use our inclusion, exclusion, recursive definition. In that inclusion exclusion, we divided it into these layers, and at every step we started with the null set and we said include or exclude. And again include or exclude. So here include or exclude C1 in this step. So this is C1 or exclude C1. Here include or exclude C2. Here include or exclude C3. So each step is include or exclude Ci. And suppose my example problem is, and my leaf nodes are those where I will create leaf nodes where I will either the remaining portion cannot meet the cost, or I have exhausted the remaining list, etc., etc. So we have done this before, and let us just quickly do it on our case study. And our case study, if you remember, was the coin set C was 8, 6, 5, 2, 1, and V was 11. And if we draw up the recursion tree, then the recursion tree where N1, where 0 nodes were selected, then we either take 8 or we exclude 8, and if we take 8 or exclude 8, then 1 in this N2, 1 node is selected. In N3, 0 nodes are selected. Then we could include 6 or exclude 6. But we know that if we include 6, this cost will become 14. So this node is rejected. If we exclude 6, then N3 we still have 1 node taken, because 8 is taken, 6 is excluded. And then now we can take 5 or exclude 5. Sorry, this is 5. If we take 5, then this node N4 again does not meet. If we exclude 5, then this node N5 has got only one node selected, that is 8. Then we could take 2 or we could not take 2. If we take 2, so here we have taken 2, and if we take 2, then we know that 2 nodes in N6, now 2 nodes are selected, and the current cost of this node, here the current cost of this node was 1 node, here the current cost is 2 nodes, because I have taken 8, and in N6 I have taken 8 and 2, and I have reached this. Now on this side, if I go to N7, if I don't take 2, then I have taken only 8 and have only 1 remaining. So I cannot meet 11. So this will also go away. So from here, I can take 1 and I cannot take 1. And if I take 1, I get N8, which has got 3 cost nodes. If I don't take, I got N9, which again has got only 8 and 2, and it does not meet my requirement of 11. Similarly, if I go this side, I have not taken anything, so I can take 6 or not take 6. If I take 6, then I have chosen, so let this be N10. Let this be N10. Then I have taken 6, so I have taken 1 node. At this point in time, if I don't take 6, at this point, I see I have not taken 8, I have not taken 6, I have left with 5, 2 and 1. And 5, 2 and 1 in N11, 5, 2 and 1 will never reach my requirement of V equal to 11. So this is also gone. So at this point, I have got 2 options. I can take 5. If I take 5, I get N12, and this is 2. Like this was a goal node, similarly this is another goal node. Now if I don't take 5, then this node N13 is rejected, because if I don't take 5, 6, 2 and 1 will never reach 11, because the remaining node will never reach 11. So this is how the recursion tree is done, and among these two I have got 2 solutions, of which this is my optimal solution. If I apply depth first branch and bound, then in depth first branch and bound I will see all the nodes, because even if I go depth first branch and bound in the left to right direction, then I will first get N8 and then I will get N12. But I leave it to you to check that in the coin selection problem, if I use a priority queue and I do best first search, then in step 1, my priority queue will contain N1. In step 2, my priority queue will contain N2 and N3. Then because N3 is, so this cost is 0, this cost is 1, this cost is 0. Then N3 will be removed and I will have N2 of cost 1, N10 of cost 1 and nothing else, because the other node is a rejected node. Now I will probably take out N2, and after I take out N2, I will get N3 of cost 1 and N10 will remain of cost 1. I could take any one of them out. Let us assume that I take out N10 because N10 entered earlier. Then I will get N3 of cost 1 and N12 of cost 2. Then I will remove N3, and after I remove N3, I will have N5 of cost 1 and N12 of cost 2. After I do this, I will remove N5, and in step 5 I will have N6 of cost 2 and N12 of cost 2. And from here I can remove N6 or N12, but since N12 entered earlier, I will remove N12, and since N12 is the goal, I will find out my goal and I will find N12, and this is my goal. And as you can see that I have not explored N8. So best first search will give me an optimal way, and as you can see, this whole thing is implemented as a priority queue. So this is my priority queue. This could also be a graph. In the case the update costs will come. Update costs will come in case the recursion tree is a graph. So this is how we implement the best first branch and bound, and that is how we implement the coin selection problem. I leave it to you to think how we will do it for a max problem. So finally, there are several other related data structures for doing the operations that we need to do. So other than priority queues, we have seen binary search trees, and then we will also see what are called balanced, this is BSTs, balanced BSTs, and among these balanced BSTs are AVL trees, B trees, etc. We will also have advanced heaps. So these include binomial heaps, Fibonacci heaps, etc. And each of these are applicable for several other kinds of problems. Then we will also have things called weighted BSTs, where the access time, so this comes from frequency of access. We had seen problems related to Huffman coding and activity selection where we required frequency of access and we got greedy problems. But when greedy problems cannot be done, this is a very interesting dynamic programming algorithm to implement a data structure. And I request you to have a look at things like these. Then there are other problems, that is data structures using advanced operations. So the advanced operations include union, intersection, set difference, etc. So these will require other advanced data structures, which we shall do later on in this course. With this, we come to an end of priority queues, and we have seen that in priority queues we have the insert, we have the remove, min or max, we have the update or delete. These form my core priority queue operations. And these can be implemented by a heap data structure, whether it will be a max heap or a min heap. In case we have find, then we may need other data structures like binary search trees. In case we have union, intersection, etc., then I leave it to you to think of what data structures we will have. Moreover, these operations on priority queues, the operations could be A, provided before the algorithm, that means it is static, or it could be online. That means at every step I will tell you whether I will insert, whether I will delete, etc. And there are a large class of optimization problems including several greedy algorithms and several branch and bound algorithms which use the priority queue data structure. With this, we come to an end of our priority queue discussion. Further discussion on various other of these problems will be coming in the subsequent classes. Thank you very much.